Good morning. Thank you for inviting me, and I'm very honored to be here, especially this first Oceans Conference in China. What I hope to do here today in 30 minutes, ambitious, is to acknowledge some of the phenomenology in the ocean that we're dealing with, consider some measurement implications to measure that phenomenology and the necessity of adaptive sampling, which will be a conclusion. Examine some of the tools for that measurement, which is an appropriate focus for a technology-oriented conference. And in particular, I wanted to, there's a lot of ways you can look at the tools, and I chose to try to look at the energetics of some of the sampling methods to kind of compare and contrast them. And then finally, I'd like to finish with documenting some of the realities in the development of those tools. I think the buzzword these days is innovation. That implies certain investment and timescales that I'll talk about at the end. Why did I use the word patterns of geophysical variability? For three reasons. One is the brain, human brain is pretty much hardwired to look for patterns. And a lot of the neuroscience research these days is very enlightening in that respect. Secondly, the geophysical world, the oceans, the atmosphere, and the solid earth, are not randomly distributed. They are organized in very organized patterns, very well structured patterns. Another way to say that, which I'll get to, is that the spatial and temporal correlation scales are not, it's not a uniform distribution, they're pretty much bimodal. And thirdly, if we want to forecast skill in predicting the patterns of variability, which is an important way of managing risk, it's pattern recognition and pattern analysis that is the correct metric. It's very hard to do point measurements. It's too noisy. You really want to measure your skill in predicting the pattern of change. That is, and I'm talking about spatial patterns. So let's just go through a couple of quick, let's see if I can do this. Is there a mouse up here? Yeah. So this is an example of the plate tectonics, basically of the. Whoops. Let me go back. How do I go back? Yeah. These are all the earthquakes around the Pacific Rim from 1970 through 2010, and the size of the little bubbles are the magnitude of the volcanic eruptions. And it's just an illustration of the fact that in a boundary region where all the energy and all the action is concentrated. This is a very typical distribution of a lot of properties of the atmosphere and the oceans. And here's an example of a meridional cross-section through the Atlantic and the Pacific. Very familiar to oceanographers, of course, a WOS section. And you can see the various water masses, and there's equivalent concept of air masses, which was not a concept that was known before the Norwegian School of Meteorology coined it, or basically discovered it in part of the 20th century. So this whole concept of fronts and air masses that we take for granted every day looking at the weather is an example of what I'm talking about. There's these big areas of relatively uniform distribution, concentrated or separated by areas of high gradients. And you can see this, the Antarctic bottom water, the North Atlantic deep water, and then the upper thermocline. Here's an example of the world's oceans plotted on a temperature salinity diagram. It's not a random thing. It's amazing, actually, when you think about it. This is the entire Pacific, Atlantic, and Indian Ocean. There's different branches. The high salinity branch is the Atlantic. But, you know, it's quite well organized into very uniform regions, separated by places, very concentrated places that set, where the processes set the pattern, give the properties of these very uniform regions, deep convection regions and around the margins. Western boundary currents, another example. This is the Gulf Stream, the Kuroshio, looks very similar. A lot of very concentrated energy on the western side of the ocean basins due to well-known dynamics. Here's an example of the Arctic ice in 2013 as it retreats. And you can see that, you'll see at the end, that over here on the right is the ice edge every day, plotted as a contour. And you can see as it retreats over the season, it's not a uniform retreat. It hangs up and then it moves fast. It hangs up and moves fast in various regions. There's concentrated areas of gradients and then fairly uniform area of gradients. Again, just another example of this sort of bimodal distribution in the correlation scales that we're dealing with, which has implications for how we're going to measure things and the tools for those measurements. That's what I'm getting at. Another Arctic picture that I like a lot because I've been fascinated for years with finger rafting. Those are leads and also in the ice looking down in a visible image. And what in finger rafting, basically the plates come together. It's like real-time plate tectonics and do this kind of thing. And it's important because in those areas, almost instantaneously, the ice thickness doubles. It would take months, perhaps years, for that to happen thermodynamically. But mechanically, it happens instantly. And so that's an example of another high gradient, action-packed region separated by fairly uniform flows, okay? And then in the coastal regions, we just saw, this is certainly one of them. This is off Italy, but all coastal regions look like this. It's not a very good picture. I got kind of blurred, but this is actually chlorophyll. But you see these boundary currents, and there's influences of rivers and various kinds of mesoscale eddy structures, okay? So given, that's the world, that's the ocean, okay? I always, for many decades in my briefings, especially in the Navy and other places, I always like to start out with pictures of the ocean because that's basically keeps your feet on the ground, so to speak. That's what we're dealing with. So here we are. I'm talking. Those were just a quick survey. You can, there are a lot of different patterns you can view, and those patterns, to a certain degree, present risk. Maybe very low risk, maybe high risk, maybe it's a hurricane or a typhoon. Very organized pattern of high gradient region, and so we have the question of what are we going to do about that, and that's a lot of the reasons why we have developed the tools to measure things. And we have basically three possibilities. We can do nothing or intervene somehow or decide the risk is too uncertain and decide to get more data. And if we want to get more data, there's the way the data, there are the possibilities up on the top there. There's mobile sensors, different kinds of sensors in the ocean that are fixed and moving. There's, of course, satellite data, and then there are the databases. If we want to do prediction, not just analysis, but prediction, we need to do one more thing. We need to introduce models, because only a model can do prognostic calculations. So once you introduce the numerical models, then you have the data assimilation challenge of the various and diverse instrumentations. And then finally, if we implement the right kind of mobile controllable sensors that like AUVs represent, that enables a big feedback loop that enables you to go around this at the right time scale to drive the risk down and make good decisions. So the reason we put things in the box up there called mobile sensors, and I'm talking here about autonomous underwater vehicles in particular, was to enable this feedback loop. When I first started to get into this and develop a lot of things in that box, that feedback loop didn't exist very, very effectively. You just took what you got and made your decisions, and they probably were not very good decisions. And the modelers were not even in the picture. They were off running their model someplace else. And the observational guys were not coupled very well. So there's two parts, of course, to the feedback loop. There's the human in the loop, as they call it. And then there's, you like to move things more towards autonomy for efficiency and effectiveness. So, and that's a current area of research. That introduces a lot of challenges, and I'll get to some of those. So that's sort of the paradigm I've been working on for many years, and it really is what justifies, putting things in the in situ data box up there that are controllable remotely and are affordable. It's really to make good decisions. That's what it's all about. So, and when you implement that sort of paradigm, a whole bunch of other types of tools come into play that I won't go into here, but certainly you got optimization is one of them, and there are a lot of tools for that. And in managing risk, you have real option theory and other decision theory, and of course latency, communication, a big one, especially for underwater. Game theory if you're going to do intervention. So, okay, so let's get a little more detailed here. Let's talk about the error involved in surveying one of these high gradient zones rather than the big interior water mass or relatively uniform regions. And say it's 100 kilometers by 100 kilometers. And it has a spatial temporal correlation scale of about 3 days and spatial correlation scale 23 kilometers. This was taken from Monterey Bay region, but it's typical of almost any coastal region, okay? Mesoscale variability. And if you plot up, for various, let's say you have a survey vessel that's going to survey this thing, and things are moving in space and time, and you plot up the grid spacing, let's say you do a lawnmower sort of pattern, and the survey duration, and I put a red line there on a survey vessel that's fairly fast, like 2.8 meters a second is 5-knot vessel, so that's fast for that's not an AUV, average AUV, and you see that when you go down, you can never get below almost around 0.4 error in your grid. With one vehicle. No matter how, if you go up here, you're going to suffer because of the time it takes you, and if you go down here, you're going to suffer because of the resolution. Things are changing. So the conclusion you make from these very primitive, simple calculations is that you need more than one vehicle to get the error down. This was one of our first conclusions. You can't do this with one platform that's not even a 7.7 meter vehicle, which is really fast for the kind of vehicles we deal with. You still can't get down much below 25%. So the conclusion is you need multiple vehicles. So then you have this little situation which I illustrated schematically. There's the environment with the spatial and temporal correlation scales that I indicated. You're going to have multiple platforms, but they're never going to be dense. They're going to be, when you look at the costs and everything else, it's going to be sparse sampling. So then the question is, how do you distribute those? And that's that feedback loop. That's the adaptive sampling. You can distribute them uniformly. You can distribute them to try to get better resolution of the gradients, or you can cluster them in various ways. There's a lot of, we did some of these things, and there's a lot more to be done in this area. And these were some of the platforms that we developed to do it. You can see some of the gliders and the propeller-driven vehicles. And here's an example of an experiment in Monterey Bay, probably almost 10 years ago now, amazingly enough. There's Monterey up there in the California Current. But essentially, we had 12 gliders being controlled by a remote controller that was optimizing the spacing for those correlation scales I indicated. And they were being asynchronously controlled every time they came up, which is whenever they profiled. And we did this for a month or two off Monterey. And you can see on the right here that based on an objective analysis error map, again, a pattern type of error assessment, that, you know, as soon as there were about 10 or 12 gliders in the water, the error, the performance went way up, and essentially we were doing sampling that was adequate for that region. That's essentially what that's a measure of. Way better than one vehicle. But it took a fair amount of architecture to do this. This was not trivial. There were 3 different types of gliders reporting to 3 different institutions, Scripps, Hawaii, Alaska, UW. Then there were, you know, the controller was in Princeton. A very interesting experiment. We also learned a lot about human robot interaction, which is another area that is a frontier, I think, in that we're just about getting into. People weren't completely used to operating this way, and there were conflict resolution, you know, that had to come into some of these things about, okay, this is the best place to go next, or this is, depends what you want to do. So let's zoom out for a minute back from the coastal region to the global scale. And you know, this is the typical, this is the WOS, World Ocean Circulation Experiment, transects, and this is the Argo array of 4,000 floats in the world's oceans. And this represents 2 other ways of sampling, not AUVs. These are floats. They have a little different approach, different view of the ocean. We get different glimpses of the ocean from these various measurement systems, and the real challenge is to put them together in a very effective way. And of course, this was all done by research vessels, the classical way. So, so the conclusion from all this is that, you know, multiple complementary platforms are needed to adequately measure geophysical variability. Okay, and another thing that doesn't take you long to realize, and all the autonomous vehicle operators realize this and are wrestling with it right now, is that they're all limited by energy. You send something out in the ocean, even a research vessel is limited by energy. It has to refuel sometimes. So, you know, this is, if you run out of gas, you can have the most sophisticated sensors and everything else. It's all over. So I thought I would just try to look at some of that, the energetic, as a little exercise to see what we could come up with. Now, if you look at, let's say, a transect like one of the big 7,000-mile transects, you know, through the Atlantic, like that I showed before, and take a little 40-kilometer chunk of that, and look at the various sampling methods that I just showed. Really, a deep glider in its current form, and this is, deep glider is now pretty well operational, would sample that 40-kilometer or chunk of ocean with using 55 kilojoules of energy, including the payload, and I'm talking about simple CTD type payloads here, in 51 hours. A sea glider, which is only profiling to 1,000 meters, will approximately take the same amount of time, but use twice as much energy, 100 kilojoules, but get 10 times more resolution, but only in the upper 1,000 meters, okay? So, and the Argo floats, the Solo 2, for example, if it's drifting through there at about 10 centimeters a second, and then goes down to 2,000, that's a typical Argo profile, only uses 10 kilojoules, but you don't get as much resolution, and it takes 240 hours. The research vessel, you know, a typical hydrocast takes probably about 20 hours in those depths at least, and it's using, by my calculations, orders of 10 to the third megajoules to do that one profile. It's amazing how much energy there is in a gallon of diesel fuel. It's 146 megajoules per gallon, okay? You compare that to what these other methods of measurement are using, it's pretty overwhelming. Another example of some of the trade-offs, and these are trade-offs which I'll get to, is deploying a float in the Arctic, and this was done last summer, and the experience there, and these are all numbers, these are not theoretical numbers I'm showing. These are numbers from a lot of deployments in the ocean, a lot of hard data. This is not modeling or calculations. On top of all the energy used for profiling and getting, that I just showed you in the SOLO data, approximately 130 kilojoules were used over the 120-day period, 19-day period, looking for open water to come up and transmit the data. And this was a system that had an upward-looking sonar to do that, and looking for leads. So for this environment, you have another drain on your energy, and that's the energy that it takes to try to find someplace to come up and communicate. So the main theme about that in all of these things, I'm going to touch on that next, is you can design a system that's for just efficiency, energy efficiency, hydrodynamically or something. But the real total effectiveness of the system is a sum of three things. One, the efficiency of the design of the platform, all of its drag coefficients and propulsion, etc. The second is how you actually fly the platform, how you actually operate it. You can have a very well-designed platform and operate it poorly and use up a lot of energy stupidly. And the third big thing, and I'm going to finish up with that, is the reliability of the platform. You can have a very efficient platform, you can operate it very smartly, and if it stops working after a week, you don't get what you want. So you need all three of those, and there are compromises in all of those. So let me finish up with the global thing. Here's some interesting calculations, interesting to me anyway. For that meridional section, if you did that with deep gliders, just deep gliders, I mean, I just took one here. You could divide it amongst several of those numbers. So it takes you 16 megajoules to do that in a couple of years, 638 days. Same sort of figures, but twice as much energy for the sea glider, for the upper water column, 1,000 meters. The Argo, it's interesting, for a global survey for all of those lines, all of the WOS lines, in all three oceans, that adds up to 644 megajoules for the deep glider and 490 for the sea glider. For Argo, if you look at the Argo floats here, if they all come up at the same time, all 4,000 floats and report, that uses 39 megajoules of energy to do that, okay? And if you do the standard WOS, Glyvar sort of survey, this is an interesting number. You got, 9 orders of magnitude more energy operating from a research vessel at 4,000 gallons of diesel fuel a day. I mean, now, I'm not saying that, we should all do autonomous. These are all complementary technologies. They're all needed. But you want to figure out how to mix and match them properly. And one of the things I did not do for this talk, but, here energy is a surrogate for cost, okay? And everybody's driven in the end by cost, okay? I mean, you can go through the calculations and transfer these energy calculations to actual cost numbers, and that would be an interesting thing to do. I may do that next, but let's just look at some of the efficiency aspects, and I'm particularly just going to focus on the gliders. The energy consumption in a glider is controlled by two main variables: a loaded mass and the wetted surface of the wing to the body of the glider, okay? And the metric I'm going to use in the next 3 slides are this net transport economy, which is a very well-known metric in the transportation industry. It's basically how much energy it takes to move some mass a certain distance, okay? It's called the transport economy. It's a unit, it's a dimensionless number. But it's a good kind of way to compare things. And this is the famous flight diagram many of you are probably familiar with the net transport economy plotted here and as a function of the loaded mass, as I said, one of the primary variables. And there's 3 things that I just want you to take away from this. This plots all kinds of flying machines, from insects to 747s, and they sort of fall along a line. It's fascinating, okay? That's not a scatter plot. And it turns out that the gliders that I just showed, which are purple and yellow there, are plotted there, and they have an NT of about between 1 and 10 for a loaded mass of about 300 grams. And they're not as efficient as natural flyers by a half order of magnitude. And of course, the natural flyers have had millions of years of evolution to get this right, so it's a pretty high standard. But on the other hand, they weren't designed to be efficient. That's the interesting thing. The first generation gliders were designed as virtual moorings. That was the first proposals, to do profiles through the water column, not glide efficiently, but to do profiles, and that you pay a price for that. And that, the second point is you can design a kind of a flying wing form factor, which has larger wetted area, surface, wing to surface area, and you can get an order of magnitude better efficiency just by doing that, and that has been done. These are real data points, again, not models or calculations from simulations. These are all measured in the ocean. And the third point is that again, this is this trade-off I was talking about. The flying wing is 43% more efficient, flies through the water that much more efficiently than the gliders you're familiar with. But the other ones are faster. So you always had this trade-off between speed and efficiency. There's the iron triangle is the you get speed, range, and endurance. Pick two. It's like the old iron triangle of good, fast, and cheap. Pick two. You only get two. Don't worry about all the numbers here. I'm sorry, I apologize for all these numbers, but just wanted to give you a feeling for what you can get if you use a thermal glider, which harvests energy from the ocean thermocline, and there are prototypes of this that have been built. You can get NTEs down to the order of 10 to the minus 6, which gives you a 35,000 kilometer range. So there's a lot of bang for the buck to go this direction for long-term, large-scale surveying, okay? And so that's an area that we should continue. When you talk about platforms that are driven by mechanical propulsors, like propellers and fins and things like that, not buoyancy engines, you can also look at the power, or it's equivalent to the transport efficiency, versus displacement of the platform instead of loaded mass. And again, it's amazing because things fall along a straight line. It's not a scatter diagram. This is pretty well organized. And the point I wanted to make here, the right part of this plot, you can see up there in the blue, is the fixed blade rotating propulsion systems, and the left part are the bio-inspired, biomimetic flapping fin kind of, what nature actually does. And we try to emulate poorly. And the point I wanted to make here, and this is another trade-off, you see another line up, you see transiting is the main line, which is of course what most vehicles do. And the price you pay for having a very maneuverable vehicle, which is what the flapping fin kind of propulsion gives you, is about an order of magnitude less efficient. Okay, that's the trade-off. If you want a maneuvering vehicle, then that's the kind of trade-off you have to pay. But for a lot of applications, that's a good trade to make. And in nature, it's done by different red and white muscle groups in fish. White muscle is generally used for maneuvering, and red muscle for propulsion. And the low aspect ratio rigid flap fin has been the most successful to date. A lot of more work to be done on this. And finally, the same sort of plot can be done for high-speed surface vessels. And the reason I bring this, again, transport efficiency, and this is the inverse of the one before, so high efficiency is up this way rather than down this way. But main reason I wanted to mention this is because you know, if you want to just design a very efficient surface vehicle, you can put yourself somewhere on here, and there's a lot of the different ones up there. However, if you want to design a vehicle that is part of a system that involves docking and recharging underwater autonomous vehicles, you have other trade-offs you want to make. And the biggest one is stability in the wave field. And if you're going to trade that, you're going to be somewhere in the middle of this rather than at the high efficiency end, because, and here's some examples of some subsurface hulls for a swath vehicle to do exactly that we designed. And so that's a trade-off that, you know, the vehicle could be more efficient, but it may not do the job for stability in a real wave field. So there's a number of trade-offs. I just wanted to mention this in passing very quickly. I'm not going to go into it at all, but, you know, I said, you know, that the system efficiency is three things. Well, here are two of them: what you move, you know, how well designed it is hydrodynamically, and how you do it, how you pilot it, how you control it. And it turns out, of course, that motion controllers are motion controllers. The one I'm using right now as I speak to you, and you're using in all those animals in the bio chart, are not PID controllers. They're completely different control mechanisms. And there's a lot to be learned from that. We haven't, none of the vehicles I know of, well, very few of them that operate right now, the autonomous vehicles are using controllers that are anything close to what biology uses. And there's an interesting postulate here if you look into the details of what happens in your neurons when you control stuff that has been put forth. Again, postulate that autonomy is a consequence of the self-regulation property of these nonlinear oscillators. I just put that up there because another magic buzzword these days is autonomy. Everybody uses this: innovation, autonomy. There's several of them, and it's not meant. It's hard to define, but probably haven't seen this definition yet. That's my guess. So I'm going to stretch your mind here. This is a keynote talk, right? So, okay. The last point I wanted to make, which is the third part of the triangle there, you know, is if you want, you know, it's not just how well designed something is or how well you control it, but also how reliable it is. And I felt like this is very important because there are a lot of misconceptions about this. And I include in the United States and the United States Navy and a lot of other places about what it takes to get out here to a reliable product. Look at the bottom scale there. And the misconception is this big hump here between R&D and reliable product. Okay, it takes, this is money on this axis. It takes much more money and investment and time. Look at the time scales of these things. 10 to 15 years, not unusual in research. And again, this is based on a lot of, just go back and look where things came from and how long it took to get there. How much you need to invest to go from research to a reliable product. And my experience, you can, with a fairly simple system, you can reach fairly high levels of reliability fairly quickly with the right sort of investment. For a complex system, which is most of the big underwater vehicles I would classify as fairly complex machines, if the testing is well funded, you could probably get them to be reliable. And I'm going to give you an example of what I mean by well funded here in a second. If it's underfunded, not only will you never reach reliability, but you may start turning around. I mean, you're chasing your tail there. So, and this is, the important thing here is to pay attention to the scales, okay? And in order to get some real meat into that, what I took was the data, and it's a tremendous data set, and it's, I think, analogous, using unmanned aerial vehicles, in particular the Predator, Hunter, and the Pioneer, but in particular the Predator has 50,000 hours on it now. Okay, it's an unmanned platform. I don't think it's as equally as complex as any underwater vehicle. What's the experience in terms of mean time between failures of that community? I mean, I think it's very analogous to what if you analyze the data and don't worry about the numbers there, just look down here. The mean time between failure goes up by about an hour for every 1,000 hours flown. This is what the experience has been over the past 10 or 15 years. So if you want to increase from 28 to 60, which is a very typical specification that you see in acquisition programs, at least in the US, okay? The platform has to have 60 hours mean time between failure. That's specified, okay, as in the RFP. For the Predator, required 30,000 hours of flight time to go from 28 to 60. That's data, okay? And I don't think unmanned underwater vehicles are any easier, okay? So what I did, and again, don't pay attention to details, I took the same met numbers and said, well, if you had a big vehicle and you had to get that much flight time in the water, that much water time, and you had to use a ship to do it, and it was a big enough vehicle, you needed a ship, what would that cost? Well, I went through some, quick and dirty calculations. It would cost you about $800 million to get up to 60 hours mean time between failure. No budget I know of in the U.S. has this. That's why they don't work, okay? So you can quibble with the numbers, but it's a large number. It's a large number, and that's based on similar type platforms and data available. So don't underestimate what it costs and the time it takes. And here's my final slide, which is, don't look at, this has been published in Oceanography Society magazine years ago. It's one I put together for the glider development. All those gliders you saw, this is what happened. Well, this is 15 years on here before we got up to, persistence reliable persistence in the water of 18 weeks, 19 weeks. Now it's 8 months, 10 months. And there were a lot of experiments and a lot of different, publications and all kinds of things. I don't want to go through the detail. You can read the paper if you want to do that. I just wanted to mention that this is consistent with the Predator data, consistent completely. And it has nothing to do, those data sets are independent. The time scale and the number of hours that went into that are very consistent. And in many cases, a lot of people contribute to these things. It's not a one institution deal. This is another reason everybody talks about collaboration. This is my example of why collaboration is important. You can accumulate these hours a lot of ways, and everybody can contribute to accumulating them and getting the reliability up. And it's too big of a number and too long and for generally speaking, for one institution, even one country to do. So to me, this is what collaboration means in a very concrete sense. Everybody getting into hours and learning and putting that information together and making a reliable measurement system that works in the ocean to sample the scales that I was talking about, this bimodal distribution of scales that we have to deal with. So, and the adaptive sampling and all of that. So it's just another way of thinking about why collaboration is so important. Finally, I'll just put a plug in for my, here's my summary. Forgot about that. Basically what I just said, I would say that the frontiers, where we go from here, I'd say, we have first generation platforms. They haven't really reached economies of scale. They're still too expensive, in my opinion. That's another thing where collaboration could come into play. Everybody wants their own little thing, and you're going to make them in little batches. They're always going to be expensive. Okay, if there's some way of coordinating that, or essentially growing the market, and it gets back to what the comments about standardization and that kind of stuff. There's certainly a lot of room for second generation platforms. Efficiency, diversity, energy harvesting, all the things I mentioned, autonomy. But don't forget the major investments that are needed to bring those to reliable products. And again, if you're going to conclude you need multiple platforms, which I hope I made the case for very quickly and briefly, then that brings into the fact that you have to know how to control and do cooperative behavior amongst those platforms. I mean, adaptive sampling is all about that. You don't just throw a bunch of platforms. I mean, Argo is an example of one extreme where there's no cooperative behavior. You're just floating around doing stuff. But that's not the most efficient way to do it. And finally, I mentioned adaptive sampling there and all of the things that implies. I just finish up by saying that some of these figures are from chapters in a new Handbook of Ocean Engineering that's coming out next month that I edited one part of. It's got 14 chapters. And some of these things I mentioned, and some of them, a lot I didn't mention, are in there. I tried to bring out, a lot of stuff that was kind of known and in gray literature and other places so it would get out into the community. And they're just finally, after years of they're finally, I think it's going to be published next month. So, it's a big book. This is just one part of it. But I'm proud of this part. It's got a lot of good stuff in it and a lot of more details about what I talked about. So stand by for that. And with that, I'll take questions or comments or whatever.
Thank you, Tom.
Yeah.
I think we have time for one or two quick questions.